In today's video, we're going to go through all the problems in homework 3. And homework 3 contains 3 topics. The first 3 problems are related to the first topic, which is the pressure forces on a flat surfaces. And the problem 4 is related to pressure forces on a curved surface. And the last 2 problems are related to calculating the buoyant forces. Now let's take a look at the first problem. And in this problem, we have a submerged round window in a seawater tank. We know the diameter of this window is 0.8 meter. We know the top of the window is under the water surface 2 meters. And we also know the window is angled at 60 degrees with respect to the horizontal. We also know the specific gravity is 1.03 for the seawater. So we can calculate specific weight for the seawater is 10,100 Newton per cubic meter. So in this problem, we need to calculate the first is the force exerted on the window in kilonewton. And we also need to locate the corresponding center pressure, which is distance between the center pressure and the centroid. Let's solve the hydraulic force first. So to do that, first we need to calculate the delta Z, which is the depth of the centroid. So the centroid is here. So its depth should equals to the h plus, we need to calculate the distance of this part, right? So it equals to the 0.5 times the diameter of the window times the sine 60 degree. So it should equals to the h is 2 meter plus 0.5 times 0.8 times square 3 over 2. It equals to 2.346 meter. Okay, so the next step, we calculate the hydrostatic force at the centroid. It should equals to the specific weight of the seawater times the depth of the centroid is delta Z. We just calculate this value, it equals to 10,100. So it times 2.346 meter. It should equals to 23.7 kilopascal. In the end, we can calculate the resultant force. It equals to P bar times A. A is area of that window. So it equals to 23.7 times 1/4 times pi times the diameter square, so it's 0.8. So finally, we can get the hydrostatic force. It equals to 11.9 kilonewton. So we solved the first question. Now let's solve the second one, which is to calculate YCP minus Y bar. To do that, first we need to calculate the area moment of inertia. It's based on the figure 8.1, it equals to 1/4 times pi times d/2 to the power of 4. So it equals to 1/4 times pi times 0.8/2 to the power of 4. It equals to 0.0201. Now, the next step, we should calculate the distance from the centroid to the surface. It's y bar. The y bar, it should equals to the half of the diameter plus this distance, right? So it's 0.5 times diameter plus h over sine theta is 0.5 times 0.8 plus h is 2 meter. The sine theta is, okay, so I just put it here. So then after we calculate it, we got the y bar, it equals to 2.709 meter. Now next step, we can calculate the distance between the center of pressure and the centroid. It equals to the area moment of inertia divided by the y bar times a, based on the equation 3.33. So we just calculate the inertia is 0.0201 divided by the 2.709 times area is 1/4 times pi times the diameter is 0.8 squared. So in the end, we can get its distance is 0.01476 meter. Okay, so this is the result for our first problem. Okay, so the problem 2, we have a rectangular gate is hinged at the water line, and we have the length of the gate that above the water line, and we have the distance from the water line to the bottom of the gate, and we also know the height of the gate and the specific weight of water. And in this problem, we want to know how much forces we exerted on the bottom of the gate can keep this gate closed. So to solve this problem, first we need to calculate the hydrostatic force, which is the Fp. The hydrostatic force should equals to the pressure at centroid of area times the area. So the pressure at the centroid of area, it equals to 0.5 times the specific weight of water times h. And the area is the h times b. So it should equals to the 0.5 times 9,810 times 2 meter, and then times 2 meter times 2. So we get the hydrostatic force, it equals to 39240, which is in Newton. Okay, so the next step, we can calculate the force. Okay, so because our gate, we want to keep the gate closed. So when the gate is closed, the moment at the hinge should equals to 0. And because the gate is a rectangular, we can know that the location of the center of the pressure should equals to the 2/3 of h, because h is 2 meter, so it should equals to the 4/3 meter. Okay, so because the moment it equals to 0, we have two forces exerted on the gate. So one is the hydrostatic pressure, right? And we define the counterclockwise is positive. So we calculate the moment is use the force times its distance to the hinge, which is YCP. And because the force of the direction of this force is clockwise, so we minus the force times distance, it should equals to h, so it will equals to 0. We calculate the value of Fp is times is YCP is what we YCP is here is 4/3 minus F is what we want to know, and H is 2. It equals to 0. Okay, so after we solve this equation, we can get the force is 26,160 Newton. Okay, so this is the result for the second problem. Now let's move on to the third problem. In this problem, there is a submerged closed gate. When the water level goes up at a moment, the gate will automatically open. In this problem, we know the difference from the pivot to the top of the gate, which is 0.6 L, and the distance from the pivot to the bottom of the gate is 0.6 L. And we know when the water level goes up, the h will increase. The h is the distance between the top of the gate to the water level. And when the h goes up, so the location of the center pressure will also goes up. So when it moves to the at the pivot, so the gate will automatically open. In this problem, we want to represent the h in terms of L. So first, to solve this problem, we need to calculate the distance between the location of the center of pressure to the centroid. So we calculate this distance when the gate opens. So the location of the center pressure when the gate opens, so the distance should equals to the h plus 0.6 L because it's right at the pivot. Okay, so the location of the centroid, it should equals to the h plus 0.5 times 0.6 L plus 0.4 L. Okay, so after we calculate this equation, we could get it equals to 0.1 L. Then we use the equation, the formula, to calculate this distance. So this formula is 3.33. So the distance should equals to the area moment of inertia divided by the location of the centroid times the area. So the moment of inertia, it equals to 1/12 times L times L to the power of 3 divided by h plus, so it is the 0.5 L times the area because it's square gate, so the area is L to the power of 2. So we will get the L squared over 6L plus 12H. Okay, after we combine the result from the first and the second equation, we will get 0.1 L, it equals to L squared over 6L plus 12H. Then we will get the H, it equals to 1/3 times L. So this is a result for the problem 3. In problem 4, we have a hemisphere dorm submerged under the water. So in this problem, we know the distance from the water level, from the water line to the top of the dorm, which is y1, it equals to 1 meter. And Y2 is the diameter of this dorm. It equals to 2 meter. And we assume the temperature is 10 Celsius degree. So based on that, we can search the value on the table 8.5 to determine the specific weight of water is 9,810 Newton per cubic meter. In this problem, we need to determine the horizontal and vertical force exerted on the dorm to keep it in place. And we also need to identify its corresponding direction of the force. And we also need to identify the line of the action of the horizontal component of force. So let's solve the horizontal component first. So to do that, first we need to determine the delta z, which is the depth of centroid first. So the centroid is over there, so the depth of the centroid should equals to y1 plus half of the y2. Y1 is 1 meter and y2 is 2 meter. So the delta z is 2 meter. And then we calculate the hydrostatic force at centroid is P bar. It equals to the specific weight of water times the depth of centroid. It equals to 9,810 times 2 equals to 19.62 kilopascal. And then we calculate the horizontal component of force. It equals to P bar times the area. It equals to 19.62 times 1/4 times pi times the diameter. So the diameter is y2, so we can directly bring the value to d, which is 2 here. So it should equals to 61.64 kilonewton. And because the horizontal component of the hydrostatic force its direction is to the right, so to keep it in position, the corresponding force exerted on the dorm should to the left. Now let's calculate the vertical component of the force. So first we need to determine the volume of the half sphere. It equals to 1/2 times 1/3 times 4 pi times d/2 to the power of 3. And because we know the d is 2 meter, so after we calculate this equation, it equals to 2.094 cubic meter. And then we can calculate resultant force. It equals to the volume times the specific weight of water. So it equals to 2.094 times 9,810. It equals to 20.54 kilonewton. And because the vertical component of the hydrostatic pressure is going up, so to keep it in place, the force exerted on the door should go downward. And then in the next step, we should calculate the center of pressure minus the location of the centroid. So it should equals to the area moment of inertia divided by the y bar times a. It equals to pi times 1 to the power of 4 divided by 4, and then divided by 2 times pi times 1 to the power of 2. So it equals to 0.125 meter. So the location of the center of pressure should below a horizontal line. With 0.125 meter. And passing through the dome center. Okay, now take a look at the problem 5. In this problem, we have a submerged spherical steel, and we know the diameter of this sphere is 1.2 meter, and the distance from the water line to the top of the sphere is 50 meter. And because it is in a seawater, based on the table 8.4, we can determine its corresponding specific weight of the seawater is 10,070 Newton per cubic meter. And regarding to the forces, we have like 4 forces exerted on the sphere. The first one is the force of buoyant, and the direction of this force is go up. And the second force is the weight of the sphere, which is equals to 1,800 Newton. And it also has the force exerted on the chain, the anchor chain. It equals to 5,000 Newton. And we need to determine the weight of the scrap. So to solve this problem, first we need to determine the buoyant force first. So the FB, it equals to the specific weight of seawater times the volume of the sphere. So it equals to 10,070 times pi times the diameter, which is 1.2 to the power of 3 divided by 6. So it equals to 9,111 Newton. Then in the next step, we can calculate the weight of scrap. Because this sphere is in a stable situation, so the force exerted on this sphere should equals to 0. So we know the buoyant force, it should equals to the weight of the sphere plus the force exerted on the anchor chain plus the weight of the scrap. So FB it equals to 9,111. It should equals to is 1800 plus the T is 5,000 Newton plus the weight of scrap. After we solve this equation, we can get the weight of the scrap. It equals to 2,310 Newton. So this is the result for the problem 5. Now let's take a look at the problem 6. In problem 6, we have a rectangular in a 2-liquid reservoir. This rectangular is 3L high, and the width of this rectangular is 6L. And we also know the density of this block, it equals to 0.75 density of the water. For the first liquid, we know its specific gravity is 1. And the specific gravity of the second liquid is 1.2. And we also know the length submerged of this block in the first liquid is L, and the length of this rectangular submerged in the second liquid is Y. So we need to determine the parameter of D. So in this plot, we can see the D should equals to the L plus Y. So in the end, we should figure out how do we represent Y. Now let's solve this problem. Because this block is stable, so the vertical forces exerted on this block should equals to 0. There are 2 forces. The first force is the buoyant force. The direction of this force is upward, and another force is the weight of this block. So the direction of this force is going down, which means the sum of the vertical forces it equals to 0. So the buoyant force minus the weight of the block should equals to 0. The buoyant force should equals to P times A, and the weight of the block it equals to the specific weight of the block times the volume of the block. It equals to 0. So the buoyant force are from 2 different liquids. So for the first liquid, the buoyant force it equals to the specific weight of water times the length times the area of this block. The buoyant force from the second liquid is equals to the 1.2 times the specific weight of water times corresponding length is Y, and then times the area of the block. And then we calculate the weight of the block is specific weight of block times the height of this block is 3L, and then times the area, it equals to 0. So after we solve this equation, we can get the y it equals to 1.042 times L. And then we can determine the d, because the d it equals to L plus y. So the d it equals to 2.042 L.